This is lecture 14 on the wave nature of light. In the picture we see a rainbow, and we see that light of different colours appears to come from different positions in the sky. Of course, the light is all coming from directly behind the viewer, coming from the sun. And as we'll see in this lecture, as the light passes through raindrops in the sky, its path is bent by different amounts. We've dealt with this phenomenon when we looked at Snell's law in a previous lecture, but here we'll see that the index of refraction depends upon the wavelength, and this is one way in which we can measure the wavelength of light. And so in the rest of this lecture we're going to explore some of the other consequences, and then in our second lecture this week we will look at diffraction, which is another consequence of the wave nature of light. So there are four consequences of light behaving like a wave. We've seen the general picture of the electromagnetic spectrum already. We've seen that radio waves, visible light, infrared, X-rays and so forth are all electromagnetic waves. They all travel at the same speed. We've seen that that speed changes when the wave travels through different materials, and we've seen that the only real difference between those different parts of the spectrum is the wavelength. We've also looked at the top item on this list, polarization. We've seen that these waves really do exist, and they really do vibrate up and down or side to side, and polarized sunglasses or polarized filters can be used to sort out the direction of oscillation of the waves. So now we're going to look at dispersion and diffraction and interference. And so to do this, we're going to invoke a principle known as Huygens principle, which suggests that every point on a wave front, which is waves spreading out from a source, is itself a source of little spherical wavelets. And if we have that picture in our mind, we'll be able to understand some of these other properties in more detail. Then we're going to look at a famous experiment in the history of science, Young's double slit experiment, and we'll come back and look at rainbows, and hopefully at some point we'll get to look at anti-reflection coatings that you might see on eyeglasses, camera lenses, microscopes, that sort of thing. So, light as a wave. So in order to understand how light waves behave under certain conditions, we're going to look at how other waves behave. So if you remember, light is a certain type of wave. It's a transverse wave, meaning that direction of oscillation is perpendicular to the direction of propagation, and that's the same for waves on water, ocean waves for example. So here in this picture we see waves entering a small cove on the coastline. So the waves are entering from the top right, and then they hit on this small hole, and they spread out into the lagoon that is formed inside this cove. And if we look at how the waves spread out, we see that although they came in parallel with the shore, the waves spreading out inside the cove are round, they're circular, and they all appear as though they came from the mouth of the cove. And so this phenomenon is called diffraction. And the very same things happens with sound and many other different types of waves. And so one consequence you can immediately see is that any place on the sand on the inside of that cove will see waves rippling towards it, even though it may be completely behind the rocks. And so this is the same reason why when you stand in a room you can hear somebody talking in another room, even though you cannot necessarily see the speaker, because the sound waves spread out as they pass through an opening, and so they essentially appear to sound as though they came from the opening. And so we'll see this happening with light also. And so Huygens' principle is the idea that every point on the incoming wavefront is a source of a new set of waves. And so the incoming wavefront is the ocean waves hitting the mouth of the cove, and then Huygens' principle says that that opening is just a point on the wavefront, and all the waves thereafter will appear to have come from that point. And all information about where they came from before that is actually lost, which we'll look at in more detail as we go on. So here is Huygens' principle drawn a different way. So we have a wave front, waves coming from a source labeled S. So the direction of propagation of the waves are given by the red arrows. So if these were rays of light, we would just be drawing straight lines in the direction of those red arrows, lots and lots and lots of them all spreading out. The wave front then is always perpendicular to the wave propagation. And Huygens' principle says that every point on that wavefront, all those little dots that have been labelled in there, we could imagine each one of them, or any other dots that we chose to pick, as being sources of new waves. And as the wave moves forward, it can be shown that if there were little sources of waves at each of those points, they would merge together to form yet another wavefront propagating out. So Huygens' principle was used long ago in the history of science to explain something that we've studied without thinking about too much. We used Snell's law to calculate the angle by which a ray of light bends when it passes from one transparent medium to another, but we never really tried to explain why that happened. So Huygens principle can be used to explain this in terms of the wavefront propagating through the air in this particular picture and then striking the water. And because the speed of the waves is slower in the second medium, say water in this case, than it is in the first medium, which might be air, the waves will interfere in some way with each other and lead to the path of the waves bending. This isn't a very satisfactory explanation either, and a more satisfactory explanation had to wait until Albert Einstein came along and explained why it is that rays of light bend the way that they do. So we'll study the theory of relativity in a few weeks for those of you who want a deeper explanation that doesn't require thinking about waves interfering with each other. So for now you can look in the textbook if you want to know more about how Huygens principle can be used to derive Snell's law, but it can indeed, and it does yield the same familiar Snell's law. So now we're going to look at dispersion. So the visible part of the spectrum consists of wavelengths about 400 nanometers to about 750 nanometers. Some people can see a bit more, some people can see a bit less. You might have noticed that some light never looks very well focused. So for example, UV light is not focused very well by the human eye. Very, very long wavelength red light is also not focused terribly well by the human eye. And so this tells us that the lens in the eye, when it focuses the light, it doesn't do a great job of focusing light of all wavelengths perfectly well. So we've looked at this before, we called it chromatic aberration, and in the design of lenses and microscopes and telescopes, it's regarded as a problem. But of course it also can be regarded as the solution to another problem, which is that if light of different wavelengths is focused in different places by a given lens, that means that you can use that phenomenon to measure the wavelength of the light very, very accurately. So all these numbers that we've been talking about, 400 nanometers, 600 nanometers, and so forth, if any of you are wondering, well, how the heck do you measure something so small? You don't obviously hold a ruler up against it. Now we're going to figure out how. So, dispersion by a prism. So, wavelength dependence of the refractive index is why a prism will split the visible light into a rainbow of colors. And this is also why a lens will focus light of different wavelengths in different places. So we already know that light rays bend towards the normal when entering a medium with a higher refractive index, and that rays bend away from the normal when exiting. So what we're now going to introduce is the extra information that shorter wavelengths, that is, wavelengths toward the blue or the violet end of the spectrum, are bent by a larger angle than the long ones. So long wavelength light can pass through a prism, like in this picture, only bending from its original path by a very small amount. But if we look at violet light that comes along in the same incident path, it bends by a much greater amount, and so ends up on a different position when the rays come out, and all the colours on the in-between part of the spectrum lie in order: red, orange, yellow, green, blue, all the way up to violet. And so the angled faces of the prism just serve to amplify this effect. This effect occurs whenever light passes through a transparent medium. It could be a window, it could be the lenses of a pair of glasses, it could be a drinking glass, it could be anything. The special thing about the prism is just that the angles of the faces are chosen to amplify the effect so that the colours are spread out by a larger amount. There are other configurations that would tend to make the light spread out by a smaller amount. So this graph here is called the dispersion relation, and it shows the relationship between wavelength of the light and the refractive index. And so on the x-axis we have the visible part of the spectrum only, and on the y-axis we have the refractive index. So we talked in this course repeatedly about saying that glass usually has a refractive index of about 1.5. So there is 1.5. And we see that a certain type of glass, silicate crown glass, which is a very common type of glass, has a refractive index of about 1.5, no matter what the wavelength. But we do see that at the short end of the spectrum, in the violet and blue, the refractive index is bigger. It's about 1.52 at 400 nanometers. And then by the time we get down to the red at 700 nanometers, it's exactly 1.5. If we look at some of the other types of glass, we see a very, very similar pattern. So the dispersion relation is not the same for all of these different types of glass. And so, in fact, the fact that the dispersion relation is different for different glass types means that you can make things like achromatic doublets, which we talked about before if you want to go and look at your notes, which are a way of making camera lenses with multiple pieces of glass in them so that the dispersion is corrected. So dispersion is useful for things like prisms, spectrographs, diamond rings, things that you want to sparkle and split the light up, and it's terrible for things where you don't want the light to be split up, so things like telescopes, microscopes, and spectacles. So there are ways to fix dispersion for those cases, and there are ways to amplify dispersion for the cases where we want to use dispersion. So here is nature's prism, the rainbow. So actual rainbows are created by dispersion and internal reflection in tiny drops of water up in the sky, which you probably all know. What you probably don't know, perhaps, is that there's a special angle for rainbows to form from water droplets, which is 42 degrees. And I believe there's going to be a homework problem coming up for you to calculate the so-called rainbow angle. So here in this picture we see a diagram, not to scale, of how the rainbow forms. So imagine a particular raindrop up in the sky. We imagine sunlight coming from the sun up here. The sunlight strikes the raindrop. It bends towards the normal. Inside the drop, it then is internally reflected at the rear of the drop. So we know that the law of reflection would govern the angles there. And then it bounces back onto the face of the raindrop, and then it bends away from the normal as it exits. And so, because the violet light, the short wavelength light, is bent more than the long wavelength light, we see that the red light comes out following a certain path, which might in this particular case land in somebody's eye, but the violet light from that particular raindrop will miss the person, they go over their head and they will never see it. And so, when the person looks up on this certain sight line, they see red. If they want to see violet, they would have to look at a raindrop that's lowered down, such that the violet light, which bent by this much steeper angle, enters their eye, and for that particular raindrop they won't see the red light, it will go miss down and land by their feet or something. And so, if we look through these two different raindrops, this person will see red coming from the top raindrop, and they'll see violet coming from the bottom raindrop, and raindrops that happen to be in between will show the various other different colours, right? So each individual raindrop is casting a complete rainbow, but you only see one wavelength from each one of them, and so the fact that there's a whole lot of them stacked up above one another leads to the formation of the rainbow. And so you can well imagine that the angle through which the raindrops scatter is determined by this business about Snell's law and the refractive index, and so that's how you would go about calculating the size of the rainbow in the sky. And so it can be shown that rainbows are always 42 degrees across. And if the atmosphere were made out of something else, like methane or ammonia, like it might be on other planets, I guess they would have rainbows, but they would have a different angle, a different size. So that might be a way that you could actually find out what the atmosphere of something else is made of. So the next slide is another rainbow picture. So we see that red is always on the outside and violet is always on the inside. We often see that there is a second rainbow, double rainbow, on the outside, looping around. And on that one, if you look at the colours, you'll see that they're inside out. So if you want to go and figure out why that is, you can go and study that for yourself. That's quite interesting as well. There's another odd phenomenon, which is that outside of the rainbow, the sky is always darker than it is inside the rainbow, which must also be related to scattering somehow. Some of that light that went into the raindrops and got scattered into different directions. So here's a question for you to study, so I'll just leave it up for a minute, and you can always go and read the textbook and come back to it. So now we return to our picture of the cove and the light spreading out from a point